Okay, while the next speaker sits up, I'm going to use the title and the author. The next talk is going to be a CompCert compiler that preserves cryptographic constant time. Remi, Hutin from ENS when Irisa? Yes, sorry, we present. Sorry. Irisa. Okay.
So thanks for the introduction. I will present to you some joint work with Sandrine Blasi and David Pichandi. So during this work, we are focusing on the preservation of a security property which is called Cryptographic constant time, which is a popular countermeasure against timing side channel attacks. Okay, so first I'm gonna give you some backgrounds on side channel attacks. So it's basically a class of attack in which an attacker would use some external data in order to deduce some sensitive information about the system. So the kind of external data an attacker can use can be the power consumption of a hardware, or maybe the one that we will focus on is the time computation takes to perform. So more precisely, the cryptographic primitive implementation are shown to be particularly vulnerable to this kind of attacks, and that's why there exists also countermeasure to protect against this kind of attacks. So the one we are focusing on is cryptographic constant time, which consists in not writing any kind of constructs in your program whose execution time will depend on a secret data. For example, you don't want to write any branching whose condition depends on a secret, or you don't want to write any kind of memory access whose address depends on a secret. So complying to this restriction is a programming policy which is called cryptographic constant time. So about static verification of this property, there have been several tools that have been built in order to verify that especially cryptographic libraries follow this constraint in with programming policy. But it turns out that checking that low-level implementation actually comply to this policy has shown to be very difficult. Meanwhile, at the high level, the verification is achievable, but then needs to be combined with a secure compiler. So the idea is that we would like your secure compiler to show that if you compile a program P which is constant time with respect to what I've just shown before, that therefore the compiled program also respects the constant time policy. So does real-life compilers actually preserve this constant time policy? Well, the answer is no. I will give you two examples of real-life compilers that break this property. So I have some code here with three functions, simple functions. The first one just takes two parameters x and y and a boolean b, and will branch on the boolean b and return either x or y. The two other functions just below are actually semantically equivalent. They perform the same operation, returning x or y just depending on the value of b. But this time in a branchless way, using arithmetic for the first one and bitwise operation for the second one. So if your boolean b is a secret, you would say that the first function is not constant time as it performs the branching on the boolean, while the two other looks safe because there is no explicit branching in the function. But if you compile this three function with the C-long compiler and these options, it turns out that the exact same code is produced for the three functions, which don't need to understand the details, but there's a jump right here and a branching. So that's a kind of behavior that we want to avoid in a secure compiler. Second example, this time with the GCC compiler, we have a very simple program. I've declared two variables x and y. The first one is an unsigned long integer. The second one is a float value. And I just cast the second one into the first one. And here on the right is the produced assembly code. So again, there are two branchings, and that's something that we want to avoid in a compiler. So in our work, we are focusing on. So I'm just giving a bit of background on CompCert here. So first, it's a realistic compiler written in Coq. It's also an optimizing compiler, and it targets several architectures, but I will only focus on the x86 architecture here. And also, so the CompCert compiler is proved in Coq and states the following theorem, which we can sum up as such. So if we have a source program S that successfully compiled to C, then both these programs have the same behavior. Alright, so this contribution that was presented yesterday during the POPL conference was about actually formally verifying that the CompCert compiler preserves this constant time policy. So there was a talk yesterday at the POPL conference that was focusing on the proof methodology that we have followed in order to prove that CompCert preserves constant time. But actually, before that, the CompCert version that we started working on, which is the version 3.4, did not actually preserve the constant time policy. So the first thing that we had to do was to modify the compiler, and this is what I will focus on during this talk. Okay, so during the rest of this talk, I will give you first some details on the CompCert architecture, because I will need to explain some parts of the compiler that we modified. Then I will show you some example of where the compiler actually breaks the property we are interested in, and I will use that as a motivating example to then present actually what we changed in the compiler. Alright, so this is an overview of the CompCert compiler. So it's a compiler that compiles C code down to assembly code. But during the compilation, it goes through several internal representations, so intermediate languages, such as C light, C minor, etc. Just to give you an overview of that, the first languages of the compiler are actually structured languages, structured with statements and instruction. The intermediate languages are presented as a control flow graph, and the last languages consist of just a linear list of instructions to represent the program. Also, I've set the border between the front end here, the front end and the back end of the compiler about here for the purpose of my talk. The idea is that the front end part will be independent on the target architecture you are compiling the program to, and the back end part is dependent on the architecture. Alright, so I will first focus on this specific transformation that happens during the compilation, which is called the operation section. So it's a part of the compilation that whose goal is to compile the operation from the source language that are here, which are the usual operations that you're used to, such as arithmetic operations, comparison, etc., and compile it to what the processor can actually compute in about one instruction. So that's the goal of this transformation, and for most operations it goes well, but for some of them there is no actual operation in the instruction set of the processor that can directly represent the operation you are trying to compile. So an example of such an operation is a conversion from unsigned integer to a float value. So this is a problematic transformation because there is no such operation in the x86 architecture that can perform this operation. But there is one that can perform a conversion from signed int to float value. And here I'm presenting the pseudocode that the compiler will introduce if you try to compile a program which is performing such an operation. What it will do, actually, it will use what I've written as int to float, which is a primitive that uses signed int to float conversion, which we can use. So the idea is that we are trying to convert this x, which is an unsigned int, to a float, but we cannot use directly. We can only use it if we are under this constant, which is 2 to the power 31. So if we are under this constant, we can use the primitive, and if we are not, we must perform a shift, convert it, and shift back to the right value. Alright, no need to understand the details, but what you can notice is that we are introducing a branching, which is something that we want to avoid. So here is the issue now. We are at this point of the compilation, and we need what is called the standard thing that is called a selection operation, something that can select one of two values in a branchless way. So there are several ways that this can be implemented, using, for example, arithmetic operators, bitwise operations, or another way of implementing it is a specific x86 instruction, which is called the CMove, but that we can only use at the end of the compilation process, because it's something that which is only defined in the CompCert compiler, but only appear at the assembly level. So the x86 CMove, which stands for conditional move, is an instruction which is first commonly used in cryptographic implementation, and which has a very simple semantic that I give informally here. The semantic of a CMove for condition C and two integer register R1 and R2. So the semantics of that it will move the value of the register R2 to the register R1 if C is true. But the interesting thing about the CMove is that it does that in a constant time way. So it's a good thing to implement our selection operation. So what we've done is that instead of modifying every intermediate languages on the backend of the compiler, we actually implemented this selection operation directly as one of the operations that are supported by the backend of the compiler. So it is a representation which is shared by all the intermediate languages, and implementing this selection operation directly as one of these operations allowed us to bypass all the backend languages. So we didn't have much to change except for the beginning of the backend and the end of the backend. And so our new selection operation performed as such. It takes a condition and two expressions E1 and E2, and it's again informal semantics. Is to first evaluate the expression E1, then fully evaluate E2, and then get both the returning values, and after that branchessly select the correct returning value. So after that we only had to modify the very last part of the CompCert compiler, which is a generation of the assembly code. Intuitively we are done to okay, so thanks to some previous optimization done by the CompCert compiler, we can we want to compile the selection between R1 and R2 and store that in the same register R1, which is recycled by the CompCert compiler. And this can be done directly using one CMove instruction. So the idea here is that we are performing a CMove from R2 to R1, which will only occur if the condition C is false here. Alright, so that's the general idea, but sometimes it's a bit more complex than that, because it only works for what is called the testable conditions, which is something introduced by CompCert, but which represents what the x86 hardware can actually. So for most comparisons at this level, it can be done directly, just as I saw with one CMove. Actually, some comparisons are a bit more complex than that, and will require a software workaround that will introduce some logical operators, such as an AND operator or OR operator, that was not present in the source language. If we are introducing an AND operator, it goes well, we can just perform two sequential. But in the case of an OR operator, we didn't find any direct solution, but the solution that we have adopted is that we prevent this case from happening by earlier in the compilation, preventing these cases to be generated. Okay. So now in the end, we have implemented this new selection operation. The built-in function that were previously introducing branching. So the first idea would be to directly replace the branching here by a selection operation. So actually it's not that simple because there are two issues now. The first one is that we will always fully compute both branches that we were not always computing before. So here in this branch, we will, in this code, we will always compute the first branch, but there is an issue because we are computing the float to int conversion, which is not defined for every x, which is an unsigned int. But here the most important issue is that this select is defined over float values here, because we perform the float conversion and then perform the select. But the the select operation only performs on integers because so does the cmove instruction. So, well, after a bit of workaround, we came up with a different solution. Here we are performing two select operations before any kind of conversion. We are selecting from the value 0 and minus c, which is this constant, and x minus c. All these values will always be in the correct definition interval with respect to the condition of the selection, and we will then convert to float values above these values, perform some the subtraction, so the subtraction between these two values, and well, this is a correct implementation for our unsigned int to float operation, and it is actually the most efficient one we have came up to. Alright. So to conclude, we have implemented this new operation in the CompCert compiler, so it's the backend of the CompCert compiler. So it also came with all the proof of correctness of the change that we have done in the compiler, which I didn't present here. So the idea is that we only had to modify two of the passes of the backend compiler, only the very beginning of it and the very end of the backend, and that all these changes that I've presented later allowed us to prove that the CompCert compiler, our modified CompCert compiler, is constant time preserving, which is what yesterday's talk was about. Also, these changes have been included in the last version of CompCert, so with a few modifications. Also, it's important to notice that Xavier also introduced a new built-in operation which is accessible this time from the source language, and that later maps to this selection operation I've presented, therefore allowing the programmer user to perform some selection operation directly from the source program. Okay, that's it. Thank you.
Okay, we have some time for questions. Yes,
so can you comment on what definition you use for constant time in the source language?
You mean the definition for constant time? Okay, so there is a semantic definition of it. So it's well, you can sum up it by preventing any insertion in the control flow of secret dependent branches. I'm not sure.
So it's, oh I see, okay, but you are not concerned about memory accesses?
Yes, we are actually, but it turns out that we didn't have to modify anything in this regard in the CompCert compiler. So the only part that were breaking our property was what I've presented here. I mean, there are more examples, but I've only showed one example here.
Okay. But all of the examples are sort of this kind?
Yes, they are quite similar to this kind of example.
I didn't see who was first, so okay.
Okay, so just a quick comment again on constant time. So one requirement that you kind of didn't comment about is you also need to ensure that instructions whose execution time depends on you not executed in secret.
I'm sorry, I'm not.
So if you have like, I don't know, if you're doing the multiplication,
Uh-huh.
and the execution time of the multiplication depends on
Yeah,
whether
okay.
one of the things is 0 or not, then you have to ensure that secret input is not used as an argument there.
Okay.
I mean, I don't know, just wondering, are you accounting for that? Or?
Okay, so our model is that here the multiplication won't depend on the operand of the
In practice it does. That's
Yeah,
the problem.
so that was my
On many architectures it does.
Well, I'm not exactly sure about how it works, but this is our model. So
okay, so you kind of assume that all assembly instructions take the same.
yeah, that's it. So same goes for the CMove instruction, which actually has been shown to be
Yeah, no, it's CMove and
I'm just want to add that if you are interested by the multiplication that takes something, it's very easy to adapt.
yeah,
You can find the programs very easily in the different
I mean that was kind of my understanding. I mean that was what I was understanding.
More questions? Yeah. How do you know what your secrets are? To state secret independence, you need the notion of secret.
okay. So here we don't know about the compiler doesn't know about the secrets. That ensures that we are not introducing any new branching. So therefore, no new branching on secrets.
No new branching on anything,
Yes, that's it.
because you don't know what's secret.
Yes, that's it.
More questions? Is there?
I really like this kind of work. I'm curious if you have, and totally like, just shoot me down. If there are lessons or insights that you think that we can use when looking at Clang and algorithms.
Can you speak up
Yes,
there?
yes. Are there like insights from doing this work, from going through this that we can instill into like looking at, if I want to go use Clang, right? I know for sure Clang actually produces, and I know in which ways it is because of the select instruction. But I don't think it's only the select instruction. I think there are other things. I'm curious if there were some insights that came out of like doing this work, or like go look at those 4 optimization passes. Those might be
Okay, maybe to simplify it, like there are some particular insights that may be applicable to other compilers as well, like some certain optimization passes that break.
Well, I'm not too familiar with it, so I'm not sure I can answer your question. But maybe we can discuss it later.
Okay, we been told by the tech guys that we might be able to actually to listen to the talk from Aslan that before we had to cut off. So now we're gonna try, and we hope it's gonna work.